All right, welcome everyone to this lecture on regression analysis with R. My name is Elijah Pia from Ghana. I am an economist by profession. I'm also a certified data science professional. I love everything about R and data science in particular. And so it is one of the very reasons why you always see me smiling. If you want to reach me, that is my email shown on the screen. We are delivering presentations on statistical inference. And so far, we've considered 2 out of 12. And you can see them right there on the screen. And today, we are looking at regression analysis. So the goals for this lesson would be to understand what regression analysis is and what we mean by linear regression. We will be able to establish causality between variables and look at how one variable causes the other, and also learn to predict one variable using another. I would like to take you to a discipline known as econometrics. Econometrics shares very similar characteristics with statistics. So I would like to take you to that particular discipline so we can visit regression analysis from that standpoint. So econometrics literally means economic measurement. And technically, the metrics aspect of the name is what is referred to as the measurement. So econometrics means we are combining mathematics and statistics with economic theory. And so if we look at a definition given by one Arthur in 1964, econometrics is a social science in which the tools of economic theory, which are mathematics and statistics, are applied to the analysis of economic phenomena. There is what we call the classical methodology of econometric analysis. We start with the first one as the statement of theory or the hypothesis. So, for example, the famous law of demand in economics is such that quantity demanded is inversely related to price. And for that matter, the thing is with consumers, when price increases, you are going to demand less. And if price decreases, you're going to demand more. There is also the consumption theory, which states that consumption is positively related to income. And so when your income increases, you're going to consume more. If your income decreases, you're going to consume less. So this is the consumption theory. So after stating the theory, you would go ahead and specify the mathematical model of that theory. And so if we look at the second theory, which is consumption is positively related to income, then the mathematical model would be C equals A plus BY. This is called the consumption function, where the C represents consumption expenditure, Y is income, A and B are known as the parameters. A is the intercept and B is called the slope. Now in economics, the A represents autonomous consumption, that part of the consumption function that doesn't depend on income. And the B is called the marginal propensity to consume. Well, the economics terms, we will just reserve them for now. So let us understand that this is a function. The A is the intercept and B is the slope. So after specifying the mathematical model, we go ahead and specify the econometric model. So the econometric model will take this form, Y equals, then we use the Greek counterpart as parameters. So beta 1 plus beta 2x plus, then we add another term called U. If we compare this econometric model with the mathematical model stated for the consumption theory, then we would most find out that the Y in the econometric model represents the C in the mathematical model. So the Y there represents consumption. The beta 1 is the intercept. Beta 2 is the slope. X in the econometric model is the income in the mathematical model. The U term that we have added to the econometric model is known as the unobserved factors. Those are other factors that affect consumption but are not captured by this econometric model. So typical example of factors that can also affect consumption would be the size of the family, would be employment level of maybe the household head. It could be the number of dependents in the family. All these are capable of affecting consumption, but they were not captured, so we deposit all these other factors into the U term that we have added to the econometric model. Sometimes, in order to make it as simple as it can be, econometric models can be of the form y equals a plus bx, then plus our usual e. Now, in the econometric model stated earlier, we use the u, but this time around, if you see the one in the box, it is an e. So we can use any other parameter or alphabet as the unobserved factor. So sometimes we use the u, sometimes we use e, sometimes we use the epsilon. Okay, so it depends, but at least we understand clearly that the u added to the econometric model, the e in this case, would represent all other factors that have not been captured by the model. So after specifying the econometric model, we go ahead and obtain the data. Because I'm in Ghana, of course, I can source data if it happens to be studies in Ghana. I can source the data from the Ghana Statistical Service. We also have international databases like the World Development Indicators, the World Bank data, and all those sort of databases. You can go there, source for information. Sometimes you can also go to the field and then collect data by issuing questionnaires or conducting interviews. So you have to obtain the data, and afterwards, you would go ahead and estimate the econometric model that you specified. And so if you recall the econometric model that we specify for the consumption theory, if we estimate using the data we have obtained, and the beta 1, which is the intercept, was found to be 17.24, and the beta 2, or the slope, is 8.97. When we fix it right into the econometric model, we have y equals 17.24 plus 8.97x. Now, in this case, you will notice that the u term of the econometric model vanishes. Later on, we'll understand why it needs to vanish after estimation. So this becomes the regression equation that we would have obtained following the estimation of the model using the data that we source from our databases. So once we have estimated this regression equation, we go ahead and conduct the next step, which is known as hypothesis testing. The reason is that we will need to find out whether the beta 1 and the beta 2, the intercept and slope that we have estimated, are significant or not. So we ask the question, is beta 1, which is equal to 17.24, significant? Is beta 2, 8.97 significant? So what we do is to test for hypothesis. So we formulate the hypothesis such that the null hypothesis will state that the parameter which we have estimated is not significant, but the alternative would mean it is significant. So in the end, if we end up rejecting the null hypothesis, then we know that the estimates that we have derived is actually significant. Let's box on. After you have tested the hypothesis and realize that your estimates were found to be significant, then you can go ahead and use that model that you have estimated for forecasting and prediction. So a typical example is the estimation of the regression equation. What you would do is, we remember the y represents consumption, the x is the income. So if you have an income level of $12 and you substitute into the regression model, you end up getting $124.88 level for consumption. And then if your income is $30, you can also substitute that into the equation, and then you're getting 286.34 consumption. So when you have your econometric model, then you can fix in different values of the independent variable, like income in this case, and then estimate the consumption levels of at those income levels. So your model can now qualify for forecasting and prediction. After it has gone through all these processes and it's able to forecast or predict, then we can use the model for control or policy purposes. So in such a case, maybe a government may be interested in knowing what level of income that would keep consumption expenditure at a certain amount. In that case, you can use it to formulate such policies and keep consumption at a desired level in the economy. So these are the methodologies of econometrics that we need to go through. And so the focus of regression models is to solve business and economic problems. And typical examples include, maybe we are trying to look at how inflation affects economic growth. Also, we can also want to look into how taxation affects business performance. So we have an economic problem, we have a business problem, and regression model is there to solve it for us. So what is regression analysis? Regression analysis is the study of the dependence of one variable, which is known as the dependent variable, on one or more other variables known as the independent variables, with the aim of estimating the mean or predicting the mean of the dependent variable based on the known values of the independent variables. This is regression analysis. So a typical example is attributed to Frank Galton. He actually started this regression thing. Now, he had something we call the universal law of regression. It had to do with height. He was interested in finding out how the average height of sons changes given the father's height. In such a case, he would want to use data on the father's height or the known values of the father's height in order to predict the average height of sons. In that case, the height of sons become the dependent variable and the father's height would become the independent variable. So we are using the known values of the father's height to predict or estimate the mean of the height of sons. So a typical econometric model reflecting this Frank Galton study of height would be this y, where the y would represent the height of sons, which is the dependent variable. And then the x would be the father's height. We already know that the beta 1 and beta 2 are known as the intercept and slope of the econometric model of that equation. Now, the u parameter that we add to the econometric model represents the unobserved factors, other factors that we think also affect height of sons but are not captured in the model, like maybe nutrition, of course, can also influence the height of sons, or maybe the genotype can also influence the height of sons. So all these other factors, we just deposit them into the u parameter and add it to the econometric model. There are some terminologies and notation that we need to use. We've been hearing dependent variable and independent variable. So other names that we can give to dependent variable is explained variable. In that case, your independent variable becomes explanatory variable. So we can also have predictant for the dependent variable and then predictor for the independent variable. We can also have regressant, regressor, outcome, covariate, controlled variable, and control variable. So these are some of the terminologies that we use with dependent variable, independent variable, and the ones that are commonly used, you'll be hearing of predictors, explanatory variables, and all those other things. So there are two types of regression models. We have simple versus multiple regression. Now, simple regression, it is where we are looking at the study of one dependent variable on only one independent variable. So for instance, we might be interested in looking at how consumption depends on income. So we are using income to predict consumption. So here we have only one independent variable. And so that is called a simple regression model. We also have multiple regression analysis. In that case, we would have several independent variables, and we are looking at how these several independent variables affect that dependent variable. So a typical example could be, we are studying consumption on, let's say, income, wealth, inflation, all these are factors affecting consumption. So that is multiple regression analysis. We have been hearing the term U parameter, which is the unobserved factors. So in a typical econometric model, we said that the U represents unobserved factors. In fact, we can also call it the error term or the disturbance term in the econometric model. How is it an error term? Why is it a disturbance term? Why do we even have to include these in regression models? So the significance of the error term stands for many reasons. One of them is the vagueness of theory, or maybe the theory might be incomplete. Like for instance, the consumption theory that we use in economics is just trying to say that income affects consumption. But we know that there are other factors apart from income that also affect consumption. Yet this consumption theory limits it to only income. And so that is why economics likes the term, all other things being equal, the ceteris paribus in Latin effect. So they like to state that sort of a phrase, all other things being equal, income affects consumption. All other things being equal, price affects quantity demanded. But there are other factors. So when you have incomplete theory, you've not accounted for maybe other variables that also affect the dependent variable. And so we just use the U parameter there as a substitute for all those other factors that have not been captured by the model. Another reason too is that data might just not be available, or the data might not be enough. When data is not enough, of course, you have a problem with generalizing or getting close to the population, right? And so there is going to be a difference between your population and the estimated model using the data that was just not enough for the estimation. So when the data available is not enough or is not available, then we have a problem with that. And so we use the U parameter there as some kind of substitute for all those other things that may emanate from unavailability of data. Another one too is core variables versus peripheral variables. Now the core variables, whenever you are estimating a model, we tend to for instance, include the very significant variables which we know affect the dependent variable, like in the consumption theory thing. So we notice that income is the very key determinant of consumption. So we consider income as a core variable. But then there are other variables that can also affect consumption, like the size of the family can also affect consumption in the family, right? So size of the family can be thought of as peripheral. They are also there to have influence on consumption, yet their kind of measurement is so, what do you call it, obscure, all right, that we normally tend not to include them in regression models if you're estimating the consumption function. So we can consider these other variables as peripheral variables. And so we might want to exclude variables whose information may just be difficult to capture in a regression model. So we just take them away, and then we use the U parameter as a substitute for it. Another thing is intrinsic randomness in human behavior. Let's keep this very simple. As long as there is a human being the subject of the study, of course, there is going to be human errors. So we have human fallibility to errors, and for that matter, we bring the U parameter there. Poor proxy variables. So sometimes you may be working on, let's say, for instance, there have been studies, because I come from economics background, there have been studies on economic growth, right? And with economic growth, we have various measures of economic growth. Some would use the gross domestic product, some would use the gross domestic product per capita, some would use maybe gross national product, maybe net national product. We have all these sort of instances there. And so when economic growth, there is data not on economic growth per se, all right? Unless, of course, we are looking at the rate of growth using GDP or something else. So we would want to use a certain variable as a substitute. That substitute is what we call the proxy. So technically, data might not be available on economic growth, but there is data on GDP per capita, GDP per whatever, and we would want to use some of these variables as proxy for economic growth. And in economics, we normally use the GDP per capita, right? So GDP per capita becomes a good proxy variable for economic growth. But if you choose any other variable that is very poor, then you are likely to encounter errors. And the reason why we include some of these U parameter in the econometric model. So if there is not enough information on a substitute variable, it becomes difficult for you to estimate your model. And so we include the U parameter there. And then the other one is principle of parsimony. Now it states that just include only relevant models, variables in the model, right? So in the estimation of consumption, you would want to include income, because yes, income may affect consumption. You may want to include wealth. You may want to include inflation, maybe price. Yes, all these are factors affecting consumption. You can include them, but something like the size of the family and any other factor that you think are irrelevant, just remove them from the system. And so use the U parameter, which is going to account for whatever error you're going to make in your model. The thing is that if I am estimating consumption and then I am able to get all factors that I believe affect consumption, every factor possible that affect consumption, then you have no error in your model. But that is practically not possible. So you would end up working with a few variables you think are relevant, and that means you are invoking the principle of parsimony in there, right? And another one is wrong functional forms. So if you are stating your regression model, if, for instance, there happens to be a non-linear relationship between two variables, but you ended up estimating the model using the linear assumption concept, then you would have stated a wrong functional form. So we say that the model is misspecified. So we need to check for some of these things, and they account for errors in regression models. So at a point in time, we would want to look at what we call population regression function. Now, in a typical econometric model, we said we are using the known values of the independent variable in order to predict or estimate the mean of the dependent variable. And that's what regression analysis is all about. So there is this kind of expectation that we create. The expectation is that we are estimating the dependent variable y with the known values of the independent variable x. That is expectation. So we can state it in functional form as this: the expected value of y given the values of x. And this expectation of y given the values of x, we are saying is functionally related to x. So it could be a linear function, it could be a non-linear function, but there is a relationship between the expectation of y and the values of x. That is why we state the econometric model. So at the end of the day, the notation for this sort of expectation being functionally related to x would be of this form. It is simply a function of x. We call this the conditional expectation function, or population regression function, or we can just say population regression for short. This is what we mean by population regression function. So if the population regression function that we want to estimate, if we assume is a linear function of the x, then it means that we are going to have the expected value of y given the values of x as the beta 1 plus beta 2x. This is where the econometric model comes into the scene. We are saying it's a function. So the beta 1 and beta 2 are known as regression coefficients. They are called intercept and slope coefficients, regression coefficients, intercept coefficient, slope coefficient. So look at how these terminologies are built up when it comes to regression models. There is the concept of linearity. Now, we have what we call linearity in the variable. So in an econometric model, we are saying that the expected value of y given the values of x is a linear function of the x. The x is the variable in there. So if you look at this econometric model, you can see that the index or the power of the variable x in this model is 2. So you can have 2 or more. Now, anytime you have a function that the highest power of the variable is 2, we call it a quadratic function. If it is 3, we call it a cubic function. If it is 4 or more, we just say it's a polynomial function. That is just to say it is not linear in terms of relationship. So this variable having the square term makes it non-linear in the variables. Then we also have another concept that we refer to as linearity in the parameters. If you look at that, we are just trying to say that the expected value of y given the values of x is a linear function of the parameters. Where are the parameters coming from? The intercept and the slope coefficient. Those are what we are talking about. So at the end of the day, if you look at this econometric model, you can see that the x variable, its power would be 1. But you know, in mathematics and statistics, we don't usually write that one. So it is linear in the variable there. But look at the power of the beta 2 parameter in there. It is squared. So it is non-linear in the parameters. And if you look at this model as well, you can also see that the highest power of the betas, the regression coefficients, is just 1, 1, 1, right? But the power of x, we have a square term there, so quadratic. In that case, this one becomes non-linear in the variables, but linear in the parameters. So when we talk about linearity in the parameters, that is the relevant choice for the estimation of regression models. So linear regression means linearity in the parameters. That is the focus. So the x values may or may not be linear. As long as the parameters are linear, we can go ahead and estimate our regression model. The moment you find out that your parameter is non-linear, you cannot estimate a regression model. That is why all the time when we state regression models, you see beta 0, beta 1, beta 2, beta 3. The assumption is that the highest power of these parameters is just 1. So linear in parameters. So every regression model would have that sort of concept. But for the variables, they can be square term, they can be cube term. Nobody really cares about that, right? There is what we call a stochastic specification. We are going to understand this sort of concept in econometrics. I've taken you to econometrics literally, okay? We are doing statistics, but it has very strong relationship with statistics and with econometrics. So for a given population Y, we said we are going to estimate the expected value, right? Yes, expected value of Y using the values of X. That is the whole thing. So you know something? Regression analysis is we are using the known values of X to estimate or predict what? The mean of the dependent variable. So when you find the mean of the dependent variable, if you take the difference between the mean and the actual value, we have a deviation from the mean. That is simply the population minus the expected value. This difference between the actual population and the estimated one is known as the error. The error. And so the population is simply the estimated plus the error term. because anytime you estimate a model, you are not getting the true population. So there is still some level of error between what you have estimated and the actual population. And so the difference between the actual and the estimate would give you that error. And so in that case, if you have the estimate and you have the error, you can add them and you will get the population. This is what this algebra is all about. So the U term is what we refer to as the stochastic error term, or the disturbance term. Stochastic error term, stochastic disturbance term. We have a lot of technical terms, in fact, today, right, in regression model. This error term is what we call the non-systematic component of the model. Somehow we'll have to get rid of it. But the one that really determines the behavior of the population is the one we are estimating. And so we call that one the systematic or the deterministic part of the model, because that is what we use for interpretation, for prediction, for control policy purposes. So we have that systematic or deterministic component of regression models, and then we have the non-systematic component. Once we have looked at the idea of population regression function, why don't we look at the sample regression function? So usually we would have wished we had data on the population. Then we would not have had so many problems with statistics and all of that. But we end up always working with samples. So samples are simply considered best approximations to the population. So we developed the concept of sample regression function because we are using sample for estimation, such that this time around, in order to differentiate this one from the population, we just introduce some accent on top of some of the variable, the dependent variable, and then the coefficient, right? So we see that accent there. What does that mean? The Y with the accent means Y hat or Y cap. So that is what it is called. And that Y hat or Y cap is simply an estimator of the expected value of the population that we are estimating, given the values of X. So the Y hat is an estimator of the population. The beta 1 hat, which is the intercept, is an estimator of beta 1. The beta 1 hat comes about because we are dealing with sample. And the beta 1 without the accent on top is simply the population parameter. So when we work with sample, we are finding the beta 1 hat, which is an estimator of the population beta. That's all. The beta 2 hat, which is the slope, would also be an estimator of the population beta 2. So the stochastic, did you hear of stochastic before? The stochastic form of the sample regression function is that we are introducing the error term, right? In every regression model, we have an error term. Now, the idea is that once you have been able to estimate the beta 1 and the beta 2, which gives you the Y hat, you can also estimate your error, because the difference between that estimated and the population gives you the error. So when you have the estimated error, you can add that error to the estimated and you get the population. So remember that we said that beta 1 hat and the beta 2 hat xi is simply the Y hat. Now, the subscript I that you see with the X is simply telling you different values of X. It's nothing extraordinary. So you can just make it beta 1, beta 2x. But we are just appending this I subscript to show you that, of course, we are not working with one sample. We are working a lot of sample size, maybe 10 or 30. So that I will represent the different values of X. So when we fix that in there, before we fix in there, that error term can also be estimated. So this time we give it the term residual term. We have the population. We estimated the estimated would not be equal to the population because we are not working with the population data. So when we take the difference between the estimated and the population, the leftover is called the residual term. That is why we give that term residual, right? The residue. So the primary objective is to estimate the population regression function, remember? But because we are going to work with sample, what do? We estimate the beta 1 and that of the beta 2. So that is the objective. So we estimate the population regression function based on the sample. So we get beta 1 hat, beta 2 hat. And so our analysis is based on a sample from some given population. That is very clear for us because we know we've been working with sample all along. So there is the question about how do we get the beta 1 and the beta 2, those estimates, how do we get them? We would use the method of ordinary least squares. It is attributed to a man called Carl Friedrich Gauss. We are not going to look at who he is. That is the name. So this man helped develop this method of ordinary least squares that we use in estimating the regression coefficient. Maybe just a little thing about how these things come about. So the whole thing is we have the population regression function. We are going to estimate it from the sample regression function because we're going to use sample. So what we do is that the beta 1 hat plus beta 2 hat x, I've used the coloring to make differentiations between what we are doing. That part, the red part, is the y hat, the estimate. So if we fix that in place of the beta 1 hat plus beta 2 hat x, we are getting the population y would be equal to the estimate, let's call it the estimated y plus the estimated error that we make. So we have this identity. So our population y equals the estimated y and that of the error term. So if we take the difference between the population and the estimated, we are getting the error. So the error, or what we call the residual term, is the difference between the actual y, the population, and the estimated one, the one we use the sample to estimate. So in which case we have the actual y minus the estimated. Now we are bringing back what the estimated really means, and that is simply the beta 1 hat plus beta 2 hat x. So we substitute that right in there, and then we have the actual y minus the beta 1 hat minus beta 2 hat x. So we want to determine this sample regression function so that it is very close to the population. All right. And remember that if the population, let's now play with some numbers. If the population is 20, then you estimate the sample and then you get 19. The difference between 20 and 19, the population and the estimated, is 1. 20 minus 19, that gives you 1. That 1 is the error, the residue, the residual error. Now, let's say someone who estimates such sort of regression thing, and the actual was 20 and you estimated you had 19, meaning your error is 1. Another person also estimates using the same sort of data and the value is 20, the population, but gets 19.5. Then the difference is going to be 0.5. So there is this difference between the error terms in these two estimated models, right? One is getting an error of 1, the other is getting an error of 0.5. Now between the 0.5 and the 1, which one is less? The 0.5 is less than that of the 1. And we would likely want to go with the model that would have that little error. Okay. So the idea is that if we want to allow the estimated value to be so close to the y, because if we had estimated the y and then we had 20, then 20 minus 20 is a 0, meaning there's no error. All right. So we will not be able to get the population in itself, but we should be very close to the y so that the difference that gives you the error would be so small that our error is minimized. So how do we go about that? We adopt what we call the sum of residuals criterion. So all we have to do is we sum the error term. So you know the algebra, we just apply the summation symbol throughout on both sides of the equation. So we have the sum of the error term equals the sum of that deviation between the population and that of the estimated. We want to make it very simple. So you know what? You would see that the sigma notation that has been introduced would have the I equals 1 to n. We have that upper and lower limit of the sigma notation. Let's take it away so that we simplify it to this form. Once this is done, then in fact, the summation of the residuals, anytime you find a deviation of a value from its mean, the sum of that deviation is always equal to 0, proven by statistics. And yeah, like that. The sum of residuals is always equal to 0 whenever you do that. So it means that the sum of residuals would become a little bit useless because we cannot advance. Now it is just 0. So what do we use 0 for? So we adopt what we call the least squares criterion. So what we do is to square the sum of error terms. So it becomes the sum of squared error, the sum of squared residuals. So we just apply a squared term to both sides of the equation. And so when that happens, we have this sort of identity there. So we only for the y hat, which is in the red color, we just fix in our beta 1 hat and the beta 2 hat. We just fix that in there. We expand the parentheses, right? And now the target is that we are going to minimize the sum of squared residuals. That is the sigma u squared. We are going to minimize that one with respect to the beta 1 and the beta 2 we are going to estimate. And so we say that the sum of squared residuals is a function of the regression coefficients, beta 1 and beta 2. Now, how do we minimize? In mathematics, anytime we want to minimize a function or maximize a function, we call it optimization problem. We have all those topics there in mathematics. Anytime we want to minimize something, we use differential calculus to do that. Now, we are not going to go into how this thing came about, but it means that we need to just differentiate the sum of squared residuals with respect to the parameters that we are estimating. Okay, so we find the derivative of the sum of squared residual with respect to the beta 1, and then we do that for respect to the beta 2. We get two identities, two equations. We solve them simultaneously through our powers of algebra, and eventually we are able to determine that if you want to calculate the slope, so if you are given x values and y values, then this is the formula that calculates the slope for you. And if you want to calculate the intercept, this is also the formula. All right, that is a method of ordinary least squares. And like I said, we aren't going to go into the algebra. Now we understand where this concept of method of ordinary least squares come about. So let's box on. Now there is an economic problem. We are looking at, for instance, a labor economist that wants to investigate whether years of education has any effect on the average hourly earnings, called wage, of people in the United States. So a years of education, does it have any effect on wage? So we formulate a regression model, and it will be of this form. So wage becomes a dependent variable, and then we regress it on education. And we'll have that relationship because the function, so we have the intercept beta naught plus the slope beta 1. Of course, we have the error term there, the u term, which is the unobserved factor. There are other factors that can also affect wage, but we're not capturing them there. So they are deposited into the u parameter there. So how do we estimate this? Of course, we need to use the method of ordinary least squares, but it's time for some programming because in R, we use the LM function. All right, the LM is an abbreviation for linear model. Linear models, linear model. At least we know that L is linear, M is model. So it takes in two set of arguments, a formula where we will look at the dependent variable and then we regress it on the independent variable. So in terms of the formula notation, you notice that there is a small squiggly line, all right, in orange color. In fact, in Greek, I think we call it tilde, tilde, however they call it, all right? So that squiggly line, let me call it tilde for convenience sake. So we will just pass the dependent variable, tilde, independent variable to the formula argument in the LM function. And then we'll specify our data, and the data simply is the name of the data frame that you are working with. So let's go and practice that. So we go right into R. And the sort of data where we can get the wage and that of the years of education happens to be in a package. And that package is called the Wooldridge package. So we have install.packages, and then we go ahead and then install the Wooldridge package. So I already have it installed. So I would go ahead and use the library function and just simply pass the Wooldridge package in there, highlight that line of code and run it. So once the Wooldridge package is loaded in R, then I would go ahead and import a data frame, which is in this package. It is known as wage 1. And you will notice that the wage 1 is the source is data from 1976 current population survey, which was collected by Henry Faber, what. So wage 1. Now I will run this line of code and my wage is imported right there. Let us look at a few observations of that. So wage 1, and then we'll go ahead and view the first 6 observations of the data frame. So if I highlight this line of code and run, we get an error instead of the first 6 observations. What is the problem? Because we could not find this function. And remember, this function is the chain operator. So how would we get it? Of course, the tidyverse. So I'll go ahead and say library and then load the tidyverse. And we know that the tidyverse houses some of our most powerful packages for data manipulation, data analysis, data visualization, and all those sort of things. So if you don't have it, you need to go ahead and then install this package. So tidyverse. So I'm just going to highlight this line of code and load it in house memory now, so I can use this chain operator for which is giving me error because it is not found. So once the package is done, then I can go ahead now and then run that line of code where we can view the first 6 observations. But because the window is too narrow to accommodate the entire columns, okay, it overflows some of them beneath it. So why don't we rather look at the tabular data? And so all we have to do is to go into the environment window and then click on wage 1, the name of the data frame, and we have a very nice tabular representation of the data frame that we're going to work with. So you notice that the very first column is called wage, and then the second column is called education. So we have our 2 variables there. So wage is the dependent variable, education is the independent variable. That's all that we need. So at this point, why don't we go ahead and initiate our model? So we estimate wage using education, which means years of education. Now, if you really want to know what each column represents, because at a point in time, let's say, for instance, you are here, NUMDEP, you might not have an idea about what this column really means. So in that case, you know what you have to do? You just have to seek help from R on this particular data. So all you say is question mark wage 1, and then run that line of code, and the documentation will be revealed to you, where we'll give you a description of where the data is coming from, how to actually import it. And then we have the format explaining how many observations we have in that data frame and how many variables are there. And then we'll give you the labels of the variable names. So the NUMDEP simply represent the number of dependents. We are using these 2 variables, average hourly earnings, and then that of education, so years of education. So all we have to do is I'm going to create an object called model, and then the LM function. Now the LM function, we said, takes in 2 arguments, formula and data. So we need to now set our formula to be equal to that formula. So the name of the package is Wooldridge. Good. Now the formula is wage, and then we bring that squiggly line. It is on your keyboard, so I believe you can identify where it is. So wage on EDUC, all right? Because those are the names of the variables we have in our data frame, wage and EDUC, education. Now I need to specify the data where these variables are coming from. So that equals wage 1, which we have imported. So if I go ahead and run this model, then let me clear the console and then print the model. So what I can do is I can type the name of the object, run, or I can just simply highlight the name of the model and run. So that by estimating this regression model, we notice that the coefficients are given. So by getting these coefficients, this one is called the intercept, clearly labeled at the top. Now, this one is the regression coefficient for education. So that is what we call the slope. Now, these were obtained using the method of ordinary least squares. So R uses OLS behind the scenes to do this computation for you without having to go through that formula sort of something. So once we have these results, then now you know how to run a linear regression model in R. Let's go back to the slides. So after we estimated the regression model, this is the result that we had. So the coefficient was found to be the coefficient, the intercept was found to be negative 0.9049. And then the beta 1, which is the coefficient for education, is 0.5414. So the regression equation from the method of ordinary least squares is now giving us wage. Remember we said when you have the sample and you estimate, what you are doing is to estimate the population. So we have that hat there. We're not using the YX naming of variables. This time around we have real names. So we say wage hat equals the intercept. We found it to be negative 0.9049 plus the slope was found to be 0.5414 education. So this is called the regression equation. How do we interpret this? Now, if the years of education, so if the years of education is simply 0, then it means that this second term would all be 0, and we're only left with the intercept. So we are saying that if years of education is 0, then the predicted average hourly earnings wage is simply the intercept, which is negative 0.9049. Now, this is not ideal because nobody is going to earn negative $0.90. So we just simply, maybe once it's negative, we just assume it is 0. So all we are trying to say is that a person earns nothing with no years of education. That is how you interpret the intercept. The slope, which happens to be the 0.5414, means that if education increases by 1 year, for every 1 year increase in education, there is going to be an increase in the average hourly earnings by 0.5414. It is also an increase because the sign of the coefficient is positive. This means there is a positive relationship between wage and education. So if education increases by 1 year, then the predicted average hourly earnings is also going to increase by 0.5414. So we are just going to say 54 cents. So the OLS regression equation is what we have found. And so we can now use this model, this equation, to predict the average hourly earnings for some years of education. So if we assume that the years of education is 10, then we can substitute it into the regression equation and we get 4.5091, which means that the the average hourly earnings is predicted to be $4.5 when a person has 10 years of education. After we have estimated this model that we have looked at, there is what we call the Gauss-Markov theorem. The theorem states that the OLS estimate, now if we are saying OLS estimate, what are they? They are simply the coefficient, the intercept, and that of the slope. So the OLS estimates, the regression coefficients are blue. That is the Gauss-Markov theorem. What does it mean? B stands for best, L for linear, U for unbiased, E for estimators. So we're just trying to say that they are best, linear, and unbiased estimators. They are blue. So the blue is just an acronym. Linear in the sense that, of course, we have been able to establish that the dependent variable is a linear function of the regression coefficient. So that is established. And if, in fact, every linear regression model means linearity in the parameters, as we have come to understand. We're also expecting that the method of ordinary least squares makes these estimates that we have obtained from the data unbiased. You know, there is this econometric and statistical algebra that explains the linearity and unbiasedness, but we are not into that. The moment we give it a term best, best means that they have the minimum variance. How do we get the standard error? It is the square root of the variance. So if you have a minimum variance, it means that, you know, you can estimate the same regression model and then get a variance of 20. The person estimates the same regression model, maybe increasing the sample size and get a variance of like 19. All right. Between 19 and a 20 variance, the 19 would be better, would be a better model than the 20 because that one is less than the 20. And that means we are minimizing the variance, the error. All right. So the minimum variance you have, then the minimum error that you are making in there. We do not want a maximum error, but we want a minimum error. That is why we minimize the sum of squared residuals with respect to the estimates. Those are where the terms are coming from. So when we say the estimates are blue, it means they are best. That means they have the minimum variance. They are linear. They are unbiased. So those estimators are like that. In every regression model, there is something that we refer to as the goodness of fit. The regression equation is a fitted equation. That is the term, the fitted equation. So how do we measure how good that equation fits the data. That's the idea. How good the model that you have estimated fits the data. And we use what we call the coefficient of determination to measure that goodness of fit. And it is commonly known as the R squared. And it lies between 0 and 1, with these two values, 0 and 1 inclusive. So if you want to look at the formula for how we calculate R squared, it's just R squared equals SSE over SST. R squared is 1 minus SSR over SST. We're not going to go into that. We're just going to explain them what they are. So let's go to the next slide. The SSE means the explained sum of squares. SSR means the residual sum of squares. SST means the total sum of squares. So the SS is sum of squares, the E is explained, R is residual, T is total. So the R squared is simply the ratio of the explained, because if you look at the first formula of R squared, it is a ratio of the explained, because we have the explained sum of squares divided by the total sum of squares. So sum of squares is simply deviations. So we are just trying to say R squared is the ratio of the explained variation to the total variation. That means the fraction of the sample variation in Y, that is a dependent variable, that is explained by a variation in the independent variable. So which means if we calculate and we get a certain level of R squared, then we can determine by how much, first of all, it fits the data, if that is the interpretation we want to look at, because we said it measures the goodness of fit. Or we can look at the explained variation to the total variation. That means what is the fraction of variation in the dependent variable that is explained by a variation in the independent variable. So how will we get this goodness of fit, this R squared? It is computed right in R. So that is not the problem. Another thing that we also need to look at is statistical significance. Now we use the concept of p-value. We have heard about this before when we're looking at the early part of statistical inference. So we use the p-value to determine significance. And p-value simply means probability value of an estimate. And this is computed right in R after you have estimated your model. There is something that we refer to as confidence level and significance level. The significance level, we said, measures the probability of rejecting the null hypothesis when it is true, and it's the complement of confidence level. We've come across this when we're looking at the concepts and applications in statistical inference. So we said that a 90% confidence level is associated with a 10% significance level, 95% confidence level associated with a 5% significance level, and 99% confidence level is associated with a 1% significance level. The remaining part of the percentage after the confidence is the significance level. That's why we say it is the complement of confidence level. So what we do is to compare the p-value with the significance level to make a decision on whether the estimate is significant or not. And the decision rule is that we use reject or do not reject. But what? Recall that when we're given the steps in the methodology of econometric analysis, we said at a point after you have estimated your beta, your regression coefficients, you will have to test for significance before you can even think about using it for prediction or forecasting or control policy purposes. Because if your estimate is not significant, then your model is not significant. That's the whole concept. So we need to test the hypothesis and determine whether it is significant or not. So what we do is that we formulate the null hypothesis and the alternative hypothesis. And the null hypothesis will state that the estimate is not significant. And the alternative will mean it is significant. So if we end up rejecting the null, then we know that the estimate is significant. Of course, we make a decision as to rejecting or not rejecting the null hypothesis. So if the p-value is less than 10%, which is 0.10, we reject the null. If it is less than 5%, we reject the null. If it is less than 1%, we reject the null hypothesis again. So we have these three significance levels that come from these three confidence levels. So if we are testing, because the common test is 95% confidence level. So it means that if we are looking at 95% confidence level, then the significance level is 5%. So if the p-value is less than this 5%, 0.05, then we reject the null hypothesis. So let's practice this. How do we do this? It is so simple in the sense that if you want to get all this information, the goodness of fit and the p-values and all those sort of things, then all you have to do is to summarize the model. So you say summary of the model that you have estimated. That's all. Not difficult. So you just say summary model, and it will give you all those sort of information. Now compare that to when we just run the model alone. It only gives you the coefficients. But now, if we go ahead and run the summary of the model, then we look at all these sort of information that we get from there. So we have a call to the formula that we've used. It gives you the distribution of the error term, the residuals. But the most important part is the coefficients and all these other information that we find down here. So from the coefficients, if you look at, this is the estimate that we had for the intercept, this is the slope. So let's look at the p-value. Now, if the p-value, if we are dealing with a 95% confidence level, then the significance level is 5%. 5% means 0.05. So this p-value is 0.187. Let's compare with 0.05. Is it less than or greater than? We say it is, if it is less than 0.05, we reject the null hypothesis. What is the null hypothesis? That the estimate is not significant. So if you reject it, it is significant. But let's look at the intercept. This is not less than 0.5. It is rather greater than 0.5. So we do not reject the null hypothesis. Therefore, the intercept is not significant in the model. If you also look at the p-value for the regression coefficient for education, the slope, it is 2e minus 16. We've explained this before, that this happens to be 2 times 10 to the power of negative 16. So we have 0.0000, 15 zeros before the 2. So it means that even in 10 decimal places, this is 0. So which means this technically is 0. 0 is less than 0.05. And for that matter, we say what? We reject the null hypothesis and conclude that the regression coefficient for education is statistically significant. Once that is established, we go ahead and say that, of course, we have the coefficient of determination. What is the R squared? Now, it is called multiple R squared. Don't worry, once you see the R squared, you are just there. So the R squared value is 0.1648, which means that if you should convert this one to percentage, 0.1648 multiplied by 100, we are getting 16.48%. It means that our regression equation fits the data by 16.48%. Maybe not so much of a good fit, because if you have 90% fit, then that is a very good thing, right? But at least this is the result we are getting for this model. So it is 16%, approximately to the nearest whole number, 16% fit. So what we are just trying to say is that any variation in education, because education is the only variable here, so any variation in education explains 16% variation in the average hourly earnings. So once we have this and we understand the goodness of fit and then how we can make decisions on significance, let us go on and look at other things. Yes, of course, we do have confidence interval. Now, we have explained this before again, that the confidence interval would be a certain defined range of values such that there is going to be a specified probability that the value of a parameter that we have estimated lies within that range. So we do have 90% confidence interval, 95% confidence interval, 99% confidence interval. How do we calculate confidence interval? Of course, we need to use the function confint. So C-O-N-F for confidence, I-N-T for interval. And it takes in the object. Object is a fitted model object. And we have already fitted that, we've called it a model. So confint model, and the level will specify which confidence interval that we are working with. So let's go right into R and calculate the confidence interval. So from here, all we have to do is to compute the confidence interval. And we are using the function called confint. It is a part of the base package, so you don't need to install any package. So the first thing is the object, and the object is model. And remember, we said the very first argument, you can just simply ignore it. And then we have a 0.95. In fact, if you should seek help from R on how this function is being used, then you would notice that the first one is object. And then the third argument is level. So it means that we are jumping over this second argument. So if you do not specify any argument name for this 0.95, R is going to think that this 0.95 is matching the second argument name here. So it means that here we now need to be explicit and say level equals 0.95. So that is a default one. So the level is the confidence level required, right? So we say 95% confidence level. When we do that, we are computing the 95% confidence interval. So when we run this, for the intercept, we get the confidence interval to be negative 2.2 up to 0.44. And if we check against the estimated, do we find the negative 0.9049 within this range? Yes. No. Yes, it is within the range. So negative 0.94 is greater than this negative 2.2. Yes, so we are approaching 0. So it is in there. So there is a specified probability that this estimate is within the range. So at least we could have had significance because it is within the confidence interval. However, in as much as our value may lie in the confidence interval, it is only a test of hypothesis that can go really into the deeper parts of the statistical estimate and then generate for you whether it is really significant or not. So this one is just an inspection of what you are likely to have in terms of significance, but that is not the decision point for establishing significance of an estimate. It is a hypothesis test that would give you the true results. So although this one lies within the confidence interval, it is still non-significant nonetheless. But the coefficient for education is 0.5414. Is it also within this range? Yes, it is. And so when we also looked at the result of the model, we noticed that it was significant. So confidence interval is just to give an idea about the range of values that we feel the estimate is going to lie in there. So as a researcher, I am 95% confidence interval that when I estimate the intercept, it is going to lie within this range. And if I estimate the slope, it's also going to lie within this range. That is all confidence interval is all about. So far, the economic problem that we just looked at was simple linear regression. Remember, we gave the difference between simple and multiple linear regression. So we only had one independent variable, which is education. Now, multiple regression means we have one dependent variable and we are regressing it on two or more independent variables. So recall that the economic problem, we only had education being the independent variable. So this is a simple regression case. But we are adding one more variable, which is experience. So we are saying that education and experience will have an influence on the weight. So the beta one would be the effect of education on weight, and the beta two would be the effect of experience on weight. So the beta one would be the slope coefficient for education, and the beta two would be the slope coefficient for experience. So a typical econometric model with two independent variables would be stated this way. Y equals beta naught plus beta 1x1 plus beta 2x2. The x1 and the x2 are called the independent variables, and the y, of course, is the dependent variable. The u is the other factors that we feel affect the dependent variable but are not captured in the model. We can also have another econometric model of this form. We have one independent variable being x, but if we suspect that there is a non-linear relationship between y and x1, then we can specify a square term of the same x1 in there. In that case, the x1 and the x1 squared still would serve as independent variables. It means that there is non-linearity in the variables. But look at the parameters. They are linear in the parameters, and so that is what regression model means. So even if you have a square term of the variable, that is not a problem. You can go ahead and estimate your regression. So a typical econometric model with k independent variables, that is never-ending number of variables in there, would be of this form, where it starts from x1, x2, up to xk, the very last variable that you can think of. So u is simply the unobserved factors. So an economic problem again, we are just going to look at how average hourly earnings and years of education and then experience are related. So suppose a labor economist now wants to investigate whether years of education and the years of experience have any effect on wage of people in the United States. Then the regression model we are going to state would be wage would be equal to beta 0 plus beta 1 education plus beta 2 experience plus the unobserved factors. So of course, we still use the LM function and then we pass it in there. This time around, the dependent variable is on the left, followed by that squiggly line. Then the independent variables on the right separated with the plus symbols. That's all. And then the data argument will simply take the name of the data frame. So let's go right into R and practice that as well. So this time around, we are looking at multiple linear regression model. And so we're just going to name this one as model 1. And then we'll use the LM function where our formula would be the weight regressed on education plus experience, and then our data argument set to the weight 1 data set. And in that weight 1 data set, we got to find out this is the experience that we are adding up. So that is as simple as it can be. So all I have to do is run this model. Let me clear the console. And then what do? When we just simply print the model, we get the coefficients for the intercept for the education and that of experience. So this is the result that we had. So we have the intercept, we have the slope coefficient for education, we have the slope coefficient for experience. And so the regression equation now becomes the weight hat would be negative 3.3905 intercept plus the coefficient education plus coefficient experience. So like we said, the intercept is not so much intuitive. So we normally avoid interpreting coefficients, the intercept anyway. So the slope of education and then the slope of years of experience would give us an idea about how they affect wage. So the slope of education is such that because it is positive, we are going to say when the years of education increases by 1 year, then the average hourly earnings wage is predicted to also increase by 0.64, holding experience constant. So we hold the other independent variables in the model constant in the interpretation. Also, a 1 year increase in experience will lead to a $0.0701 predicted increase in average hourly earnings, holding the years of education constant. So that's how we interpret this model. So once we have the regression coefficient, we can also easily predict wage for some level of education and experience. So if the years of education for an individual is 10 and that of experience is 5, then we can substitute these values in there and the predicted wage that we are getting is 3.6. So that means a person with 10 years of education and 5 years of experience is predicted to have an average hourly earnings of $3.6. So if we want to measure the goodness of fit, do you remember? Summary of model. That will give you the R squared, and there is also another thing called the adjusted R squared. We'll look at that. Then we also need to test for hypothesis, right? The t-test will determine the significance. We said we compare the p-value with the significance level. And of course, we will have to formulate hypothesis concerning the fact that the estimates are not significant for the null hypothesis. So we have this hypothesis formulation. And the summary on the model will give us all those results. Then there's one more thing. We are testing hypothesis of all population parameters. That means we are putting together all the estimates and we want to feel whether their presence in the model makes the model significant or not. So we call it the global or joint hypothesis, or we say overall significance. So we are looking at the entire model in its entirety. So we formulate the hypothesis that the beta naught equals the beta 1 equals the beta 2 equals 0, meaning all of them are 0. That means they are just not relevant to the model. They are not significant, null hypothesis. And the alternative is that even if one of them is not equal to 0, of course, it is significant. So let's go right into R and look at this. So in R, all we have to do is to do what? Summarize. So we say summary, and then we pass into it model 1. Let's clear the console, highlight this code, and run. And when we do that, we have a very holistic details. This is why R is preferred when it comes to the language of statistics. R is preferred to Python. You know, it gives you the whole thing in a very fast manner. So when we included experience in the model, we even got to realize that the intercept was significant. And so once you see the stars there, that is how you get to interpret them, right? Because they represent the significance levels. So we are saying that this one, of course, it is 1.18 times 10 to the power negative 5. So it is technically 0, even in 4 decimal places. So it's less than 0.05. So we can say the intercept is significant at 5%. It's even less than 0.01. 0.01 means a 99% confidence level. So you can reject this null hypothesis at 1% level and conclude that the intercept is significant at 1%. The coefficient for education is also significant at 1%, and the coefficient of experience is also significant at 1% as well. So these are very, very, very significant estimates that we have derived from the data we had. Then we do have the R squared. Now the R squared is 22.5 if we convert to in percentage. So 0.2252 is 22.52%, which means that our model with education and experience in there fits the entire data by 22.52%. Wow. And the R squared is 0.2222. And the approximate, right? Because if we're rounding this one to a whole number in terms of percentage, it will be 23, but this one is 22. So something that you always need to look at. The R squared and the adjusted R squared must always be close. If you get an R squared of, say, 23% in this case, and you had an adjusted R squared of maybe 9%, that is 0.09 something, then there is a problem with your model, a very huge problem with your model. So always make sure that the difference between the R squared and the adjusted R squared is not so much. Now, if you look at the summary of the first model where we had only one independent variable in there, look at the R squared. It was what? 16.48%. But if you look at the R squared, when we included experience, we have 22.52%. It is natural that the moment you increase the number of independent variables, your R squared increases. It is natural. So if you have one independent variable, you have a level of R squared. If you add another variable to that same model, you are going to get an increase in R squared. If you add another variable, you're going to get an increase in R squared like that. So what R does behind the scenes is it will find an adjusted value so that the addition of more independent variables will not lead to an explosion of the R squared and will not end up deceiving us. So the R squared is always there to compare itself with the multiple R squared all the time. So that is why we said it must be very close. So the adjusted R squared simply means when you add more independent variables, we are adjusting for the fact that there's going to be an explosion or an increase in R squared. So let's adjust it to a certain level. And if it's very close to the multiple R squared, then that is very good. All right. But if there is a significant deviation between the adjusted R squared and multiple R squared, there's something wrong with your model. So in the end, we're able to conclude that the OLS regression equation that we estimated fits the data by 23%. And we can even say that any variation in the independent variables in the model explains 23% variation in the predicted average hourly earnings. That is a wage. This one is the residual standard error. So we are just looking at how much error that you have made right here, okay? This is what normally we refer to as the mean square error, but we are not going to that. If we are into machine learning, then we'll need to go deep into the mean square error and then those sort of things, the mean absolute error and all those other things. So let's just say this is just additional information that is given to us in the model. But the most important ones to interpret, R squared is there, the significance of the coefficient, the adjusted R squared is there. And most importantly, we mentioned a global hypothesis. And it gives you an F statistic. Any test that is being conducted is associated with a certain test statistic. So we have the t-test, we have the z-score test, we have the f-test, we have chi-square, we have so many squares and those tests. So the F statistic is 75.99. Well, forget about the fact that we have a numerator degrees of freedom and a denominator degrees of freedom. If you went deep into econometric analysis or deep into statistical analysis of regression models, you would have understood where these 2 and 523 is coming from in terms of degrees of freedom. But like I said, because we are dealing with software, some of the results are given to us and we interpret the ones that are most important. We use it for our research purposes or our thesis and what have you. So we are very much interested in the p-value that we generate for the F statistic. The p-value here is 2.2e, that is 2.2 times 10 to the power negative 16, which is 0, all right? And it is less than 0.01. This one is the test of the global hypothesis. That is all the regression coefficient put together. So all this is trying to tell us is that the entire model, the overall model, is significant at 1%. If you were thinking of establishing significance at 95% confidence level, then you can say this one is significant at 5% significance level, right? So this is how we look at some of these concepts right in there.